All right, today we're diving into something that sounds like it's straight out of a sci-fi movie. It's a new system called EvoClaw, and it's built on one really radical idea. What if AI agents could evolve all on their own?
I mean, really let that sink in for a second. We're not just talking about an AI learning from data. We're talking about an AI that can fundamentally change its own abilities, its own code, while it's up and running. This isn't a Hollywood script. It's the core question EvoClaw is trying to answer. And frankly, it could change everything we think we know about autonomous systems.
So why is this even a problem we need to solve? I mean, don't we have plenty of AI agents already? Well, yeah, but here's the dirty little secret. Right now, even the smartest, most advanced AI agents are basically stuck in place.
On the one hand, you've got the agents we have today. You've probably heard of things like AutoGPT or Baby AGI. They're pretty cool for sure, but they're static. Their skills are completely fixed. If you want to teach them a new trick, a human has to pop the hood, write new code, and manually update them. But on the right, that's the dream. Agents that can actually evolve, adapting and learning on the fly, all by themselves.
And this static design, it creates this massive bottleneck. I mean, think about it. What happens when a website's API changes? The agent just breaks, useless until a human fixes it. What if you want to run an agent on a tiny smart thermostat? Forget it. The code is way too bloated. And if you're trying to manage a whole fleet of these things, it's an absolute nightmare.
So, to get around all this, the team behind EvoClaw looked to a pretty surprising place for inspiration, biology, and they came up with this absolutely brilliant concept they call the genome.
Now, what is a genome in this context? It's actually incredibly simple. It's just a text file. That's it. This file is a simple list of the agent's skills, everything it knows how to do. But here's the key. It's completely, totally separate from the agent's core engine, the part that actually does the thinking. The best way to think about it is like this. You've got the body and you've got the DNA. The body is the core program. It's written in Rust, which is super fast and efficient, and it basically never changes. It's just a reliable engine. But the DNA? That's where the magic happens. It's just a simple text file that can be edited, swapped out, and evolved to completely change what the agent does, without ever touching the body.
And you might be thinking, this DNA sounds pretty complex, right? Well, take a look. This is it. It's not crazy code. It's a simple configuration file that anyone can read. This little snippet right here tells the agent to monitor the computer's CPU and memory every 30 seconds. And if you want to change its behavior, you just change a number. That's it. Simple for us to read and super fast for a machine to understand.
And this right here is the superpower that this whole body and DNA thing unlocks. Because the skills are just in a text file, the agent can reload its own abilities while it's running. It never has to stop, it never has to restart. It can literally learn a new skill in real time with absolutely zero downtime.
Okay, so the concept is cool, right? Body, DNA, I get it. But how does this actually work? How does an agent use this to evolve out in the real world?
While the whole system is built in 3 layers, think of it like a command structure. At the very top, you have the general, an orchestrator that manages the whole fleet of agents. Down at the bottom, you have the soldiers, the agents themselves, running on different devices and doing the actual work. And connecting them all is a super lightweight messenger service that lets the orchestrator send a new genome down to any agent at any time.
Now, inside every single one of those agents is a little piece of software called the genome engine. When a new genome file comes in, it kicks off this little process. It reads the file, makes sure the instructions make sense, and then seamlessly swaps out its old skills for the new ones. It's this constant, never-ending loop of adaptation.
Now, this all sounds great in theory, but does it actually work? This is my favorite part of the whole thing, because the researchers didn't test this on some giant, expensive supercomputer. Nope. They went in the complete opposite direction.
They dug up a Raspberry Pi 1. We're talking a tiny little computer from 2012. It has a single core processor and just half a gigabyte of RAM. I mean, your smart toaster is probably more powerful than this thing. By today's standards, it's basically a museum piece.
And the result? Get this. The entire EvoClaw agent, this piece of software capable of real-time evolution, compiled down to a program that was just 3 megabytes in size. That is smaller than a single photo you'd take on your phone.
And it gets even crazier. While it was actually running, juggling 3 different skills at once, by the way, it used only 3.2 megabytes of RAM. That is just, it's ridiculously, unbelievably efficient.
Let's just put that number into perspective. Your typical AI agent, the kind you hear about all the time,
often needs hundreds of megabytes of RAM just to sit there and do nothing. EvoClaw is over 100 times more memory efficient. This isn't just a small improvement, people. This is a complete game changer for where AI can actually run.
And you might be thinking, okay, it's small, but is it stable? Well, they stress tested it. They left it running on that little Pi for 3 days straight. The result? 0 crashes, an almost non-existent failure rate, and the only failures came from network glitches, not the agent itself. And it basically didn't leak any memory. This thing is absolutely rock solid.
So, we've established this as a huge technical achievement. But what does it all mean? What does a future with tiny, efficient, evolving AI agents actually look like?
Well, the possibilities are kind of mind-blowing. Imagine your smart home devices actually getting smarter, learning your routines, and doing it all locally, so your privacy is always protected. Or think about armies of these little agents monitoring servers, each one evolving to be the perfect watchdog for its specific job. You could even have an agent that messages you and says, "Hey, I have an idea for an upgrade. Can you approve it?"
The paper even goes one step further, into some really fascinating territory. They talk about a skill marketplace. Just imagine, an agent discovers a really powerful combination of skills, a killer genome, and it could then sell or trade that DNA with other agents. You'd have a literal functioning economy of evolving AI.
And all of this brings us to one final huge question. By separating an AI's body from its DNA, EvoClaw has basically unlocked a brand new way for software to modify itself. So if an AI's code can truly evolve on its own, adapting and improving out there in the wild, where does that evolution stop?